with the slides. Okay, so Gauss's law. So Gauss's law is a technique for calculating electric fields in regions around symmetric charge distributions. Okay. So for instance, here is a sheet of charge, an infinite sheet of charge, and the electric field will be infinite plane sheet of charge. The electric field will be perpendicular to the field, and we saw what the magnitude of the field will be. So Gauss's law is a convenient way for calculating electric fields of highly symmetric charge distributions. So that's the key for highly symmetric charge distributions. And it relates electric fields at points on a closed Gaussian surface to the net charge enclosed by the surface. So what this means is, so, okay, let's, what that means is, so what Gauss's law does is, in general, so if you have a bunch of charges in a region, you can draw any enclosure, and what Gauss's law does is it relates the fields on the surface of this Gaussian surface. This surface is called a Gaussian surface after Mr. Gauss. Okay, so it relates the electric fields on the Gaussian surface to the charge inside the surface. Okay, so that's what this statement is. Gauss's law relates electric field at points on a closed Gaussian surface to the net charge enclosed by that surface. Okay. All right, so we'll define a couple of terms before we introduce Gauss's law. Okay. So here is material flux. So imagine a river flowing. And if you want to know what is the volume of water flowing through this ring, the volume of water flowing through the ring is the area of the ring times the velocity of the water. Okay, so that's how many liters per or meter cube of water per second is flowing in SI units. Okay. Now, what if the ring is at an angle like this? Okay, so what we do is we define something called an area vector. The area vector is the direction of the vector is perpendicular to the area, and the magnitude is equal to the area. Okay, so now how much water is flowing through this? Well, it turns out that the amount of water flowing, so when you have an area like this and the velocity like that, it turns out that the amount of water flowing through that ring, flow rate, is A dot V. Okay, so AV cosine theta. Now let's see if it makes sense. So for instance, let's say we make the ring like that. That is, it's pointing perpendicular to the direction of flow. Now, of course, so velocity and then angle is 90 degrees. Now the flow rate is of course 0. Okay, and that makes sense because cosine 90 is 0. Okay, so the flow rate is given by AV cosine theta, A dot V. Okay, so that's the flow rate. Okay, so now we'll use a similar idea to define something called electric flux. So this was material flux, how much material is flowing through this ring. Similarly, we'll define something called electric flux. Okay, loosely you can think of how many lines, electric field lines, are threading an area. Okay, and we'll define it exactly like that. Electric flux is denoted by phi, and the subscript E telling you it's electric flux. In a couple of chapters, we'll define magnetic flux, where we'll use a subscript B to denote magnetic fluxes. Okay. So the electric flux is, okay, in this case, since the area vector and the electric field are parallel to each other. Theta is 0, cosine 0 is 1. Anyway, the electric flux is just the magnitude of the electric field strength times the area. Okay, and you can think of this as roughly quantifying the number of field lines passing, threading that area. Okay, so now if the area is at an angle to the electric field, so in this diagram, in that diagram, okay, so the area vector was like that, and the electric field was in this direction. Okay, and okay, so the electric flux is given by E dot area. Okay, and that's what's shown here. So the area vector is there, and there's the electric field vector. So the flux through that thing is E dot A. Okay. So now we defined electric flux. Okay. Now what we'll do is we'll ask the following question. Let's say we have an enclosed surface. So here's an enclosed surface. And what we want to do is calculate the flux through this surface. Okay. And here's the rule. If field lines are coming out of the surface, we'll count them as positive. And if field lines are going into the surface, we'll count them as negative. So that'll contribute negative flux to the total flux. Okay. So what we do is, so here's a area, and we'll break this surface into small area elements. There's this area. The flux through this area is, there's the area element, and there's the electric field at that point. So it's A delta A dot E, which is that term. And then you sum over the entire surface. Okay. In the limit those area elements are small, this becomes a surface integral. This is a surface integral. Okay. And that will give you the flux through the entire surface. All right. So let me show you a simulation. All right, so there you go. These orangish lines are electric field lines. Okay, and you can see that through this area element, the flux will be negative because there's the area vector and there's the electric field vector. This angle is greater than 90 degrees, so E dot A will be negative. Okay, so this area element is contributing, there's a negative flux contribution here. This area will give you a positive contribution. There's the area vector, there's the E vector. E dot, this is an acute angle, and this will give you a positive flux. And in this case, the area vector and the E vector are perpendicular to each other, so there's no flux going through that area. Okay, so that, okay, so if you do this, the surface integral gives you the sum over all those area integral, little area elements. Okay. All right, so now we're ready for Gauss's law. Okay, so the flux through this enclosed surface, if it's an enclosed surface, we indicate the surface integral with the little circle on the integral sign. Okay, so that's standard notation. All right, so here's a surface integral on an enclosed surface. So if more lines are leaving the surface than entering it, then the net flux is positive. So if there are more lines leaving the surface than entering it, then the net flux is positive. And of course, if there are more lines entering the surface than leaving it, then the net flux is negative. So here's an example. Okay. So let's say you have a uniform electric field in a region, and we calculate the flux through this cubical box. Okay, so you can see that this phase will give you a positive flux. This phase will give you a negative flux since the area vector is pointing in that direction. And the four sides will give you zeros. Okay, so, and that's what these terms are. This is the flux through that phase. This is the flux through this phase. And the four zeros are for the four sides. And you can see that in a uniform field, the flux through this cubical box is zero. And you can actually generalize and prove it in a uniform field through any enclosed surface, the flux will be zero. Okay, so you can calculate that. All right, so here's the statement of Gauss's law. Gauss's law says net flux through any enclosed surface, net flux through any closed surface is proportional to the charge inside the surface. Okay, so the flux through an enclosed surface is equal to the charge inside the surface divided by epsilon naught. Okay, so for instance, if this were the surface, now see, there's no charge inside the surface, so there are an equal number of lines going in as coming out. So the net flux through that surface will be zero. So let's see, we have a question. Okay, so the flux through this surface is zero. Here, there's a negative charge in, so that will be negative. So the flux through this surface will be negative. And you can see that the lines are going in. The flux through this surface, there's a positive charge inside, there's a positive charge inside, so there'll be net positive flux, and you can see the flux lines are coming out of the surface. Through this big surface, okay, the net charge is zero again, okay, and the flux will be zero. There are equal number of lines coming out as coming in, okay. So that's what Gauss's law says. It relates the flux through an enclosed surface to the charge inside the surface, okay. All right, so now is a good time to pause and let you guys